Welcome to The Explainer. Today, we're diving right into what is, without a doubt, the most successful, most accurate, and honestly, the weirdest description of reality human beings have ever come up with: quantum field theory. So, where did this absolutely revolutionary idea even begin?
Well, to get why we even needed this theory, you got to go back to this massive problem physicists were staring down in the early 20th century. You see, they had these two beautiful theories that were perfect at describing their own little corners of the universe. The problem was, the moment you tried to use them together, reality just kind of broke.
And those two pillars were, of course, Einstein's special relativity, the rulebook for things moving super fast, and quantum mechanics, the rulebook for the super, super small. On their own, they were rock stars, making predictions that were proven right again and again. But they were built on ideas about reality that just could not get along.
So here's the heart of the fight. Special relativity is all about consistency. It demands that the laws of physics are the same for everyone, everywhere. Physicists call this Poincare covariance, but it just means the rules of the game can't change just because you're moving really, really fast. But the quantum world, it's all jumpy and based on probabilities. And when you try to write down the math for a quantum particle zipping along near the speed of light, that beautiful, smooth consistency of relativity, it just shattered. The equations spat out total nonsense.
And it turns out the whole problem was the picture itself. The old way of thinking was that particles, like electrons, were these tiny, solid, indestructible little balls. And sure, that idea worked just fine for slow-moving stuff, but it was the fundamental roadblock. To bring these two great theories together, physicists needed a completely new way of looking at everything, a really radical one.
And that brings us to the incredible solution: quantum field theory. The pioneers of QFT basically asked a wild question. They said, hey, what if particles aren't the fundamental thing at all? What if the real foundation of everything we see is something else entirely?
The answer they came up with was the quantum field. Just try to picture this: a fundamental substance that exists at every single point in space and time. It's everywhere, all at once. Like our source material puts it, a field is a means to hold or supply an arbitrary collection of quanta. Forget the particles for a second. The field is the reality. The field is the star of the show now.
Okay, here's the best way to get your head around this. Think of a huge, calm, invisible ocean that fills up all of space. That's a quantum field. Now, when you see a particle, say an electron, you're not actually seeing a tiny little dot. What you're seeing is a ripple, a little vibration, a little packet of energy, an excitation on the surface of that underlying electron field. The particle is just what the field does.
So, if we accept this new picture, what does it actually mean for how we understand the universe? This shift from a particle-first to a field-first reality has some truly wild consequences.
First off, it means every single type of particle has its own universe-spanning field. There's an electron field, a photon field for light, a Higgs field, the whole shebang. A single particle is just the smallest possible ripple you can have in that field. It's one quantum of energy. And because they're just ripples, particles aren't permanent anymore. The field can ripple, creating a particle from nothing, and then calm back down, making that particle vanish.
This new picture completely redefines even basic ideas like mass and spin. Mass isn't how much stuff is in a particle anymore. Nope, it's just a label for how a field's ripples interact with space-time, how much energy it costs to make a ripple. And spin? It's not a little ball spinning on its axis. It's a fundamental property of the field's own internal geometry. The particles just inherit these traits from their field.
And what about forces, like magnetism? In QFT, forces are just interactions, conversations between fields. Think about two electrons pushing each other away. What's really happening is that one electron, a ripple in the electron field, causes a new ripple in the photon field. A nearby electron field then absorbs that ripple. This little exchange, this passing of a virtual photon back and forth, is what we feel as the electromagnetic force. It's all just fields talking to each other.
Now, this all sounds incredible, right? It solves the big conflict, it gives us this elegant new picture of reality, but there was a catch, a huge one. When physicists actually tried to do the math with this new theory, they ran into a terrifying problem. The theory had a dark secret.
The answers were infinite. Seriously. When they tried to calculate how a particle interacts with its own field, a process involving something called radiative corrections, the equations just kept spitting out infinity as the answer for basic things like the mass of an electron. And obviously, things in the real world don't have infinite mass.
The theory, as it was completely and totally broken.
The solution they came up with is one of the cleverest and, let's be honest, weirdest tricks in all of physics. It's a mathematical toolkit called renormalization. It's basically a set of very careful rules for subtracting one infinity from another infinity, which sounds crazy. To some, it felt like just sweeping the problem under the rug. But what it did was cancel out all the nonsensical infinite junk and reveal the real, finite, and incredibly precise answers that were hiding underneath all along.
So why on earth did physicists accept this bizarre mathematical sleight of hand? The answer is simple. Because once they used it, quantum field theory didn't just work, it became the single most successful, most predictive theory in the history of science. Period.
And this right here is the ultimate proof. This is for a property of the electron called its magnetic moment. The top number is what quantum field theory predicts, and the bottom number is what we've measured in experiments. Just look at that. They agreed to more than 10 decimal places. That is an absolutely stunning level of agreement. It's like measuring the distance from Los Angeles to New York and getting it right to within the width of a single human hair. It's just unreal. And its success isn't just a one-off. QFT is the absolute bedrock of the standard model of particle physics, which is our current best map of reality. It predicted the existence of antimatter before anyone had ever seen it. It explains 3 of the 4 fundamental forces of nature. Put simply, QFT is the language we now use to speak with the universe on its most fundamental level.
So what holds this whole amazing framework together? Well, as our source material lays out, it's really built on a few core non-negotiable principles. Things like Poincare symmetry, which, remember, is just that idea that the laws of physics are the same everywhere, and relativistic causality, the strict rule that an effect can't happen before its cause. It's a complex picture, for sure, but it's an incredibly coherent one.
And that brings us to the big question. Quantum field theory is a monumental human achievement, but we know it's not the final story. It famously doesn't include gravity, for one thing, and there are other deep mysteries it doesn't touch. Which just leaves us to wonder, what's the next revolutionary idea? What new picture of reality, maybe as strange and profound as the quantum field itself, is waiting just around the corner for us to discover?